Have you ever wondered why an antibiotic can just completely knock out an infection for one person, but then fail, just totally fail, for someone else, even when it's the exact same bacteria? Well, that's the kind of clinical puzzle we're tackling today. We're going to play molecular detective and dig into a really fascinating case of antibiotic resistance in a common bug called Haemophilus influenzae.
Okay, so let's get right to the evidence. We've got two lab reports here for the very same bacteria. Now, the one on the right, the BLNAS, that's exactly what you want to see. The bacteria is susceptible, which means, hey, the antibiotics are working. But then you look at the one on the left, the BLNAR, and suddenly, the same bacteria is resistant to common workhorse drugs like ampicillin. So what's going on here? How is that even possible?
All right, to crack this case, we first need to understand the bacteria's little bag of tricks. It really has two main strategies for fighting back against the drugs we throw at it. So here are its two main moves. First, it can put up a shield. The bacteria literally produces an enzyme that just chews up and destroys the antibiotic. Simple, but effective. But the second one, that's a bit more clever. It's a disguise. The bacteria actually changes the very target the antibiotic is trying to hit. It's like changing the locks on a door. And our mystery today? It's all about this changing the lock strategy, which we call BLNAR.
So, how does this disguise, this changing the lock thing, actually work? Let's zoom way in, down to the molecular level, and see what the bacteria is really up to. This is where the real detective work starts. So that target we were talking about, it's a protein called penicillin-binding protein 3, or just PBP3 for short. And the best way to think about it is as a very specific, very important lock on the bacteria's cell wall. For an antibiotic, which is our key, to kill the bacteria, it absolutely has to fit perfectly into this PBP3 lock. Now here's what's so fascinating, what's so clever about this blonder mutation. It's incredibly selective. It changes the lock, yeah, but only slightly. It just subtly reshapes the one part where certain keys like amoxicillin are supposed to fit. But, and this is the key point, it doesn't completely jam the keyhole for every antibiotic. This selectivity, well, that's the crucial clue in solving our whole case.
Okay, so if the lock has changed, how do we find a key that still works? Well, it all comes down to the physical shape and size of the antibiotics themselves. Let's put two of our common options head-to-head.
This table just breaks it down perfectly. Think of amoxicillin as a small, delicate key. It needs a super precise, absolutely perfect fit to work. C4Xame, on the other hand, it's a bit bigger, a bit more robust, it's more forgiving, so you can probably see where this is going. When the bacteria mutates the lock, that's BLNAR, that delicate amoxicillin key just doesn't work anymore. But the beefier, more forgiving sulfurexime key can often still muscle its way in and get the job done.
And this visual really says it all. The bacteria has reshaped the keyhole. That small, specific amoxicillin key, it just can't get in and turn. And you might be thinking, well, what about adding clavulanic to it? But that's a shield buster. It's great against that other defense, but it can't fix a key that simply doesn't fit the lock. The larger cefuroxime key, though, can often still force its way into this newly shaped lock and make it turn. Okay, so now that we're armed with all this knowledge about locks and keys and shields, let's circle all the way back to those confusing lab results from the beginning. I promise you, it's all going to click into place now.
Right, let's walk through this. For a normal strain, BLNAs, no problem. All our keys work, susceptible across the board. For the shield strain, BLPAR, we just add our shield buster, clavulanic to amoxicillin, and boom, it works just fine. But now, look at BLNAR, our altered lock mystery, Amoxicillin-clavulanic. It fails. It's resistant. Why? Because the key doesn't fit. The shield buster can't help. But our bigger key, cefuroxime, often still works, at least against the early mutations. But as the bacteria mutates even further, you can see that even cefuroxime can start to fail. And that's when you have to bring out an even bigger, more robust key, like ceftazidime. See? This chart unlocks the whole mystery.
So what's the big takeaway here? Why does this all matter? Because it's a huge reminder that fighting bacteria isn't just a chemical battle, it's a physical one. It's about geometry. The actual shape of the drug and the shape of its target is what makes all the difference. And knowing this is absolutely critical for doctors to pick the right antibiotic and win the fight for their patients.
And that leaves us with one final, pretty sobering question. We figured out how to pick today's altered lock, but this is a constant, relentless arms race. The bacteria is always evolving, always trying to design a new, better lock. A bigger key might be the solution for today, but what about tomorrow?